you please welcome Sean O'Halpin, who's going to talk about the joy of text.
Hello, everybody. Like the joy of text, this is going to be something of a potpourri of different things, a sort of whistle-stop tour through the various bits of information that I had to learn as I was trying to get FFI ncurses to a complete state. FFI ncurses is a library that I've written, which is basically a wrapper around the ncurses library using FFI, hence the name, FFI ncurses. Okay.
Do we need to understand this so far?
No, you don't have to understand any of it at any point. Yeah. Okay, so text. What is text? It's strings of characters, and characters themselves are actually quite slippery things. We tend to have a very human sort of point of view of them, and it's obvious what a character is. But in fact, a character is really made up of a number of different conventions that we agree to. It's represented in memory as a number. Usually there's a glyph that will represent a visual symbol, and there's a mapping between those numbers and the glyphs. So, for example, the number 97 in ASCII is the lowercase a, and it can have a number of different visual representations. That's just to get that out of the way. I'm not going to go into a lot of detail about that kind of thing. There's a difference in the way that Ruby 1.8.7 and 192 represent single characters. 192 represents them as strings. 187 represents them as numbers. So this is just a little tip, a portable way of finding out what the actual ordinal number for a character is. Use the string, index it with 0, and use ORD. Okay? So that actually trips me up a lot when I'm trying to do portable programs. So I thought I'd share it with you. So what I want to look at is, how does text get into your computer? How does it get out again? And what does Ruby do with it on the way? But first, I'm going to take you back in time a little bit, and we're going to look at one of the old chestnuts, really, I think, of computing, which is the HJKL cursor key movement. People give lots of reasons why Vi, for example, uses HJKL, and I'd like us just to look at that in, just for a minute. It does have relevance, but there's Vi. That's actually NVI, which is closer to the original than Vim. The original Vi doesn't really exist anymore. This is NetHack, which is a roguelike game. One of the reasons why I wrote FFI ncurses was to be able to write this kind of game. And you see here, just by absolute fluke, it's assigned me the character of a neutral female gnomish wizard, which is uncanny, really. Yeah. Bash can be set into Vi mode with set O Vi if you really, really want to. And GNU Screen in copy mode as well does it. So why does Vi use HJKL? It's all down to this man, Bill Joy, looking very moody here in his TED photo. He actually looked a little bit more like this. If you see him, that's him up there with the beard. When he wrote Vi, that's actually when they started Sun in 1982. He wrote Vi in 1976. He was also very heavily involved in BSD. And he wrote it on the American Dream Machine. Oops, that's the wrong one. This is the American Dream Machine. The Leah Siegler ADM, which stands for American Dream Machine, 3A. And you see in the background, there's a DEC VT05, which looks very Star Trek to me. But I think there's a similarity between those two all-in-ones. So why does Vi use a cursor? HJKL for cursor movement. Some people say it's touch typing, some people say it's more ergonomic, and others say it's for efficiency reasons. But in fact, the real reason is because the Lear Siegler ADM had the cursor keys on the H, J, K, and L letters. Just on a similar note, the CD tilde to get you home. The CD will just take you home anyway, but why is the tilde used as the home character? Well, it's because of the C shell. The C shell is one of the original shells that introduced this convention of using the tilde as the home. And it's because of this man here, Bill Joy, who wrote the C shell on his American Dream machine. And if you look up at the top right-hand corner of the keyboard, you'll see a strange little knobbly thing there. And that actually is where the home key is. And you'll see that it's got a tilde on it. And that's why home is represented as a tilde. But there's something very, very intriguing in this photo, a here is button. I'd love to have a here is button on my terminal. So, one of the reasons I've taken us on that little history tour is to show you that the terminal emulator that you use every day, I hope you are all command line junkies, it has a lot of history behind it. And it's only by understanding that history that we can really make the most of it. So how does text get into a computer? Usually via a terminal emulator, in our case. That's what I'm looking at today. The terminal emulator is known as a TTY device. A TTY device, as you can see from the Linux console, if you type TTY, it's dev TTY1. Xterm is a dev PTS3, so if it's running under X, for example, it's the same under the Mac. It will be a PTS, which is a pseudo terminal, which we'll be looking at in a minute. And the reason they're called TTY is because it stands for teletype. The teletype was invented in, I think, 1905 to do stock tickers. And it gradually became a more capable machine, able to not just share stock quotes, but also to send letters both ways. So these things here, a friend of mine, her father used to operate one of these during the war, and he said that what they used to do was send each other dirty limericks to test the lines. And the reason they used dirty limericks is because they thought the Germans wouldn't understand a dirty limerick. I don't know if that's true. So the teletype is actually represented here on this diagram here in the hardware. So you've got hardware, you've got a serial line connecting to a UART driver, which is Universal Asynchronous something or other, I forget. It connects through to into the kernel via a module which imposes what's called line discipline. This is then managed by the TTY driver, and that then interacts with your user processes. And that is the system underlying pretty much, that's the system that underlies modern computers today, even the most modern Mac OS X machine. You have, it doesn't look exactly like that. It looks a little bit more like, well, not like this actually. This is a Linux console, and the Mac doesn't have a Linux console. But here again, you've got the hardware down here, a display, keyboard. Keyboard connects to the keyboard driver. Usually nowadays it's a USB, HID, human interactive device. I don't know what other kind of things they expect, like simian interactive devices perhaps. The VGA driver drives the display, and the terminal emulator, which is part of the Linux kernel, then hands that to the line discipline, which then does the same thing as the last example. I'll talk about line discipline in a minute. And here we have the situation with something like Xterm, which is kind of what I'm more interested in because it's what we really use nowadays. I mean, the Xterm here actually is sitting behind a whole stack of stuff, which is basically X Windows or the Mac OS X, yeah? GUI, which handles the hardware, the keyboard, display, and everything. What Xterm does is it connects to a pseudo terminal, a pretend terminal, which is a data structure that's set up in the kernel, which then pretends, it's got two sides. It's got a side which communicates with the user program, Xterm, talks through the line discipline module to the slave part of the pseudo terminal, which then talks to the user process. So the user process thinks it's talking to a terminal, here, the slave, and Xterm thinks it's talking to a terminal, you know, the input-output part of that. The line discipline bit is one of the things that causes lots of problems for people when they like SSH onto like old machines and things. Line discipline is the thing that provides erase, end of line handling, and it's there usually that you get things like you might use an old machine and find that instead of using backspace, it will expect you to use a hash character to delete something, and that's because the line discipline module hasn't been configured to your liking. The way you do that is with a program called STTY. But it's curious the kind of language they used in those days. It's like master, slave, and discipline. It's all a bit S&M, isn't it? Okay, so those diagrams were cribbed, not copied, cribbed, from a very, very good web page, TTY Demystified, which explains all that stuff in a lot more detail if you're interested. And it's worth finding out because it's at the heart of the systems that we use today. Yeah? So, an example. Say, for example, you wanted to script Vi externally. You could try doing something like this, like trying to pipe some text into it. If you see there, I, hello world, /e, :w, hello text, /n, :q, n. So what would that do? It would insert hello world, hit escape, and try to write it out as hello.txt and then quit. But it doesn't work. It doesn't work because Vi wants to talk to a terminal, and it checks when it starts up. But Ruby has a very handy library called PTY, which isn't terribly well known, which will enable you to talk to a program like Vi, and it will provide a pseudo terminal for you, like we saw in the diagram just a minute ago. So here you can you basically get the output, the input streams, and a PID from the PTY spawn. Then you can write to it on the input channel. And at that point, Vi thinks it's talking to a real terminal, just the same as it would be if it was talking to Xterm. You close it and then wait for it. You can also use another library, which is very handy, expect. So this is only a toy example. It spawns IRB, it then waits for the prompt. It doesn't really do much checking on it, to be honest. It then puts the string puts hello world into IRB's input, and then the string exit. And you've got to watch out for those new lines, obviously, because otherwise it won't complete the input. And then just above that, there's a thread that starts after expect finds the prompt, and this will just print out the the output from IRB. I won't demo that. Okay, so PTYs. PTYs are really, really useful things to get to grips with, I think. They're maybe a little bit complicated to start with, but it's worth having a look at them because they're used in all these different things. The terminal emulators use them, obviously. But they're also used by things like Screen and Tmux. I mean, what happens with Screen and Tmux is that the master part of the terminal is detached from the slave part. The slave part stays there talking to the process, and the master bit is then just basically deleted. And then later, Screen or Tmux will reattach another master to that, to the slave. SSH also uses it. You have the terminal that you've got when you're working at, that has a master PTY, master side of the PTY, and on the remote machine that you've SSH'd into, SSH sets up a slave PTY for you. And there's kind of a interesting little project a guy's done, a thing called Gate 1, which does all that through a web browser, but it's in Python. So I'm not sure if I should really recommend you look at it. If you want to know more about PTYs, and I think it's a really interesting part of the whole Unix, OS X, BSD world, the book to read is Advanced Programming in the Unix Environment, and you will be able to understand what this diagram means. Okay. So how does text get into your application? Well, usually it's from the keyboard. Well, that's what we're talking about today, is keyboards and screens. And a keyboard works by, you press a key, you get a key down event, key release event, and the keyboard handles debouncing, which is pressing too many times or too quickly or whatever. Where it's when the key bounces back up and it might generate another event, the keyboard will suppress that. So the keyboard and the operating system communicate really through a driver. This is the same for the Mac, for Windows and Unix. It will be talking to it over a serial port, USB or Bluetooth, for example. And generally, all keyboards will work pretty much the same way. They generate scan codes, events, which the kernel will interpret. Some operating systems, like Windows and the Mac, will let you get hold of those scan code events. Unix doesn't really, unless you want to write X code. It will translate them into key codes, and in Linux, at least, and I think BSD, well, obviously BSD as well, but the Mac as well, it will translate those into ASCII character codes. So then you've got the terminal emulator, which is basically running under a windowing system. Now, both X Windows and the Mac OS X have an incredibly complex input system, which I really didn't want to get into go into detail, so I've just left it at that. But one of the things that you do get is you are able to get key down, key up events, but you don't get those if you're writing stuff in the terminal, because the line discipline, the bit that handles line editing, arrays and all that stuff, it loses that. It just translates it into a code. Right then, once you've got through the windowing system and you've got through the line discipline, you've got into your program. And generally, you've got the C library there. So you've got to get through standard I/O, buffering. You've got to get through the locale handling. And then you've got to get through whether either you're using, whether your program underneath the hood is using getcar or getWideCar. And then, ultimately, as we're talking about Ruby here, it goes up through the Ruby I/O system to a a function called RBIO-GetC. RBIO-GetC was about, I think, 5 lines in 1.8.7, and then 192, the one where we've got all the encodings and everything, it's about 30 lines. Yeah. It's much, much more complex in 192. But it's a lot better, and it actually works now, which is good. Okay, terminal emulators. So I'm sure all of you have seen the term variable, and you've probably struggled with it at some point as well. So it usually has one of these values here. VT100, VT220, Xterm or Xterm 256 color, which the Mac is now using by default, I believe. If I'm running under the screen, you'll get the screen term value, and if you use a term under Emacs, it will call it done. What is it? So VT1, this is a VT100, which again it's got this kind of, I think there's something very iMac about these old machines. That's the VT100, which is the basis for all these escape codes and things that we use. And that's the VT220. And the VT220 is the basis of what Xterm emulates. Xterm is a terminal emulator. It's actually pretending to be one of these. It's pretending to be a real physical machine. And it does it very, very well. In fact, Xterm is really the only complete terminal emulator there is. None of the other ones really cover all the possibilities that you can do with a terminal. So, but Xterm, in its default state, is really ugly. I've made it more ugly there by using color. But you can make Xterm look quite nice. And there's things like tabs from the suckless.org, which enable you to have multiple Xterms in a tabbed interface. And the way you do that is by using X resources. And it does look a bit kind of complicated to begin with, but it's actually kind of straightforward, and it does really make sense. So if you do want to do things like real Unicode in a terminal and 256 colors in a terminal, you really want to look at Xterm and get to grips with these X resources. So the way that terminals, the way that terminals talk to the display is through escape sequences. Here's an example. That displays the word hello in color. But the problem with, and you can use ANSI color, the problem with the escape sequences is that you can't control the cursor. So you get the cursor still blinking. There's a thing called, the way that the terminal emulator understands what it is it's meant to display is through a subsystem in X called termcat and terminfo. It's the same on OS X. There's a little, very handy little program called tput, which you can use to find out how wide and how tall your terminal is. Oops, I'll leave that. Or in Ruby 1.9.3, you can use the new I/O console module, which will give you the row and column, as the last line there shows you. But the I/O console library doesn't really do an awful lot. It just gives you the ability to get a single character without buffering, or to find out the size of the window, and to change some of the line discipline things. Readline also affects how your input gets into the system. And here is a little tip for Ruby. If you want to have little keyboard macros for IRB, you can put this in your input RC. The top one will put quotes around the previous word, and the bottom one will add a require statement. So that's what I was saying about. It's a potpourri. It's a real mix of things here. But these are just the little things that I found out. If you want to find out what escape sequence a particular key generates, cat -v is a very handy little tip. That's the control. That's the code there for the control right arrow. Okay, Unicode. To do Unicode in a terminal successfully, you'll need to set your locale to a UTF-8 locale. You'll need to use a terminal emulator with UTF-8 support. That's a list of them. The only one that does real UTF-8 is Xterm. Well, no, that's not quite true. It's the only one that can display all Unicode characters. The other ones accept UTF-8 as input. But there's only one font that I've come across in any system at all that has a good coverage of Unicode characters, and that's that one. Again, that's the next resource. Okay, so quickly, a word about FFI ncursors. Those are all little bits and pieces that I learned as I was trying to get FFI ncursors finished. And what is it? It's a full-screen terminal control library. It basically enables you to do things like turn the cursor off, handle function keys, use unbuffered input, and display colors and characters anywhere on the screen, on a terminal screen. The reason I did it is because the existing ncurses Ruby system library it just didn't support Unicode really well at all. And it hadn't been maintained for a long time. I'll just quickly talk you through this example. This puts hello in the middle of the screen. Well, not at the top of the screen, actually. You require FFI ncurses. Include it here, just so we can use these methods without prefixing them. In Itzra, all these methods here map directly onto the C library ncurses methods. So you can look up any of these methods from a man in Itzra, and you'll get the C cursors information, and it's almost identical. The way that the FFI ncurses library works is that it's a direct mapping onto the C thing, the C library. Keypad standard script true just sets it to enable function key input, arrows, and all that sort of thing. Raw means that you get everything that comes in. No echo turns off echoing. Again, these are line discipline controls. So that when you press a key, it doesn't immediately echo on the terminal. Cursor set 0 turns the cursor off. Adstra hello prints the word hello, and then refresh. Because these are emulating, this is working with a terminal emulation, the refresh is the thing that actually flushes the output to the terminal. And nothing will display until you do that refresh. And then you've got getcha, which will return a single character. It's not Unicode aware. You'd have to use, there's a whole host of wide character functions too. But just a little word about the rescue and ensure thing here. The rescue is to capture exceptions, and the ensure is to make sure that you call this method endwin. If you don't, then generally what will happen is you'll get a really messed up terminal. And if that does happen, you can use stty sane or reset. Okay, very quickly, a couple of examples. This is a file viewer, which handles arrow keys and the page up, page down kind of keys. So that's showing, it's using the input. You can do things like put a little help screen on it, get rid of it with escape. You can resize the window. You can resize the window, and it will resize the text window that it's displaying. So that's an example in the FFI ncurses library. That's the kind of thing that I actually really want to be using this for. Yeah? It's like full screen applications with color and cursor addressing. But there's another one here, which is kind of the roguelike idea. So this is showing a roguelike kind of thing. It's not a game at all. It's just a map with a field of view algorithm. And that's another example in the FFI ncurses library that you can have a look at. And I'll just see if this works. It might not. Oh yeah, okay. And this is one of, is it Jamis Buck did the graph algorithms stuff? This is one of his algorithms, created a graph for me. And here's me walking around it with my field of view algorithm. Thank you very much.
Thank you, Sean. That's great. Any questions?
Paul.
Why didn't you do your presentation in ncurses? I really like that.
Man, I started writing. I started writing a slide show displayer in ncurses, but I didn't have enough time. You know. Also, I couldn't really do the diagrams in that. So I would have been switching between the real thing, the end cursor. I know, yeah, but it wouldn't fit. Yeah. Any other questions? No.
Okay, well,
Okay.
we can have a little break.
It's navigators around, it's ASCII art diagrams using the field of view.
Yes, good, yeah. I'll do that next time. Yeah. Thank you.